In the previous videos, we derived a number of Taylor series. We talked about what a Taylor series is, or Taylor or Maclaurin series is, and we derived a number of series. And we even used them in some of our previous videos to calculate certain things. So in this video, let's talk about just working with those Taylor series that we have already derived in videos, or possibly the book did it, or you might have even done it in homework or on the worksheets. And we have created a bank of what we call useful power series. And throughout this section, we're going to use those power series to answer sort of what I think of as follow-up questions. So to do things that maybe we could do without the series, but also ones that maybe we couldn't do without the series representation for the given function. So kind of just getting used to working with Taylor series and using them to answer some mathematical questions. So let's first start just with what are our useful power series? And here I have projected on the page the reference sheet that I have created for this section. And so, of course, this is actually from the previous section, just what is a Taylor series? How do we find a Taylor series? How do we represent a function with a power series if it has a power series representation? And we do that with the Taylor series, looking for the pattern in the repeated derivatives and coming up with a power series representation. And of course, if we are just centered at 0, if our a value is 0, then we call it a Maclaurin series. So I'm going to zoom in on the second page of the reference sheet. And these are the useful series that we should know. And this I took out of the book. This is the book's notation for these useful series. But we also did a number of these in the videos, or you might have done them as a homework or worksheet problem. So here is our list of our useful power series. And so you can see the one that we started with, 1 over 1 minus x. We've got our e to the x. We've got our trig functions, our logs, our inverse tangent, and then ending down here with the binomial series. So our binomial series, our expansion for 1 plus x to the p. Now, the book also includes a few more. And so here is the expanded table from the book, including the ones that we have, as well as the two, zoom in here, the two hyperbolic, sinh and cosh. And so, of course, we could find those power series representations just doing the same thing that we did for the previous one. So sinh and cosh are included in the book's more expanded formulas, and you will see those as well in the homework. So sometimes you'll see sinh and cosh in the homework, but I will not expect you to have these memorized or to use these on any sort of in-class, in-person exam. So just wanted to mention that those two are included in the textbook, and you might see those in homework, and so you can always reference, you can use this reference table anytime you need to. Okay, so let's jump into it and do a couple. All right, so for these first two examples, we just want to find a power series representation, radius of convergence, and the first 4 non-zero terms. Now, for all of these, we're going to go ahead and use those useful power series that I just mentioned and just showed you on the reference sheet. So when I come across this first one, the first thing that I think about is this inverse tangent. I see the inverse tangent of x squared. So it's not just inverse tangent of x, but I see the inverse tangent of x squared. And since I have a power series representation for the inverse tangent, what I'm thinking is, well, let's go ahead and represent the inverse tangent of x squared as a power series, and then we can multiply that power series by x, work with our power series rules and manipulations. So rather than scrolling back to our table, I just grabbed this. We just check out the table, we look at the table, or we recall, because we've already derived this one, recall that the inverse tangent of x is equal to the power series from k equals 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1. And that is true. I included, because we will need it, I included the radius of convergence that is standard for the inverse tangent that was derived when we developed that power series representation. So we're going to utilize that. We're going to say, well, f of x then is going to be equal to x times the power series of negative 1 to the k. We're substituting x squared in for x, so x squared to the 2k plus 1 divided by 2k plus 1 from k equals 0 to infinity. And this equality is going to be true for, let's write it over here, for the absolute value of x less than or equal to 1. Or another way of saying that is the radius of convergence is equal to 1. So I'll go ahead and write that. So let's keep going. This is kind of messy. We don't want to leave it in this form. So let's keep going. We've got x. This is x to the first. We're actually going to pull that in just a second. Let's pull that into the series. That's going to be distributed to every term in the series. So it's going to be x to the first times negative 1 to the k. When we take x squared to the 2k plus 1, we get 4k plus 2 divided by 2k plus 1 from k equals 0 to infinity. And this k to the first power, we could combine these two factors right here by adding their exponents. So this is going to be equal to the series from k equals 0 to infinity. We're going to have negative 1 to the k, x to the 4k plus 3, because we add the exponents, all over 2k plus 1. And so now we actually have a power series representation for x times inverse tangent of x squared. And we wanted to also find, oh, and we already have the radius of convergence. So all we were asked was for the radius of convergence. We could have checked for the interval of convergence by testing the endpoints, but we weren't asked for that. We were just asked for the radius of convergence, but we do want the first four non-zero terms. So if we want the first four non-zero terms, we're going to start plugging in our index and see what we get. So f of x is equal to, we're looking at x times the inverse tangent, a representation for x times the inverse tangent of x squared, which is equal to k equals 0 to infinity. Let's see, is there anything to simplify? I think we already got it all simplified. But we're going to start plugging in our index to see what those first four non-zero terms are. So we want to do the first four. So since the index starts at 0, that means we need k equals 0, k equals 1, k equals 2, and k equals 3. Probably don't need to space them out that much, but we've got it. So if I plug in 0, the numerator becomes negative 1 to the 0, so it's positive. So we start with a positive term, and we're going to have x to the third over 1, so just x to the third, minus, and then we're going to have x to the, when I plug in 1 for k, I get x to the 7th over 3, plus x to the, when I plug in 2, I get 11 over 2 in the denominator, and I'm just looking up here, just plugging directly into that, so that becomes 5 minus x to the, when I plug in 3, 4 times 3 is 12 plus 3, I get 15 over, and in the bottom, 7. Now, of course, those continue, but we were just asked for the first four non-zero terms. So I'll put the dot, 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 just to indicate that that does, of course, continue. But those are my first four non-zero terms. Now, if I needed to work with this function for any reason, and I wanted to make estimations, then I could use my first four non-zero terms, or go even further. If I wanted more terms, then I could use those terms. So we have both the power series representation. I should have made my box around all of it. I have both the power series representation, the first four non-zero terms, and my radius of convergence. Okay, let's take a look at another one. Suppose we want to write, same instructions as before, I won't scroll over again, but same instructions as before. Let's represent this function as a power series, find its radius of convergence, and the first four non-zero terms. So if I have g of x equals cosh of negative 2x, I am not expecting you to have the power series representation for the hyperbolic functions memorized, but we do have them in a table in the book, and so we could absolutely utilize those power series. So let's do it. I just referenced it down here. Here's the formula from the table from the book. And g of x, which is cosh of negative 2x, we are substituting negative 2x in for x in the power series representation. So this would be from k equals 0 to infinity, negative 2x to the 2k all over 2k factorial from k equals 0 to infinity. Now, the radius of convergence here, this is true for all x's less than infinity. It's kind of funny how we write that. But of course, what that means is that the radius of convergence is infinity. So x can be any number. So let's go ahead and just continue to simplify this and write out those first four non-zero. I like to get these simplified before I start plugging in to find the non-zero terms. So this is a -1 times 2. So I'm going to distribute that power 2k. So it's -1 to the 2k to each of the factors inside. 2 to the 2k and x to the 2k. Now, the reason I want to do that is because that -1 to the 2k, that's really -1 when we raise -1 to the 2k, that's -1 squared to the k. So that's really just 1 to the k, which is 1. So this -1 to the 2k right here becomes just 1. So I just wanted to show that. Just use the exponent rules there. So that just becomes 1. So we don't have a switch on this, so this becomes just k equals 0 to infinity. 2 to the 2k is actually 4 to the k, so let's simplify that as well. X to the 2k all over 2k factorial. And we wanted the first four non-zero terms, and we're starting at 0, so we'll get k equals 0, k equals 1, k equals 2, and k equals 3. And then, of course, we'll continue, but we're only asked for the first four non-zero terms. So when I do that, the first term, so at 0, we end up with 1, just 1 actually. So the first term is 1 because everything is to the 0. And remember as well, this was from previous videos, but remember that 0 factorial equals 1. Another quick little recall there. 0 factorial, I should have done that in red. One other little recall, 0 factorial equals 1. Okay, k equals 1. So when we get k equals 1, the next non-zero term would be 4 times x squared over 2 factorial. And then the next term is going to be 4 squared, so 16x to the 4th over 4 factorial. And then the next term, we're going to get 4 to the 3rd, so that's 64x to the 6th all over 6 factorial. Now that continues, and we could simplify that, plug that into our calculator, but I'm going to leave it just like that and move on to our next example. So let's go ahead and just leave that guy just as is. That's our first four non-zero terms. If we needed them to evaluate this function for any reason, we could do so. All right, let's keep moving. So let's use power series again to, in this case, instead of just representing a function, let's represent a function and then take the limit of that function as x approaches infinity. So it says use a power series. We're going to focus in on the e to the 1 over x, and we're going to use our power series expansion for e to the x to evaluate that, subtract 1, multiply by x, and then take the limit. So we want to take the limit as x is approaching infinity. We've got x times, now let's plug in our power series representation for e to the 1 over x. So e to the x, I already wrote our little recall here. E to the x is x to the k over k factorial. So we're plugging in 1 over x. So that becomes 1 over x to the k all over k factorial from k equals 0 to infinity. Then we're going to subtract 1, multiply it by x, and take the limit. So to do that, let's get this simplified, write out a couple of terms so that we can subtract 1 and multiply by x. So let's see what happens here. So we've got x, very much like we just did in the previous ones, except now we're adding a little bit more. We're going to be subtracting 1 and multiplying by x. So this becomes, of course, the power series of just 1 over x to the k times k factorial from k equals 0 to infinity minus 1. Well, when we do that, let's go out this direction since I have a little bit of space here. When we do that, let's write out a couple of terms. We end up with our first term is going to be 1. So we'll write out the first couple of non-zero terms here. So let's go k equals 0, k equals 1, k equals 2. Let's do 4 again, just like we were doing before. I think that's going to be more than we need, but let's write out the first 4 terms. So when we do that, the power series, when we plug in 0, we get 1 over, again, we got that 0 factorial there, but remember that equals 1. So we get 1 over 1, so we get 1. Then the next term, so when k equals 1, when we plug in k equals 1, we're going to get plus 1 over x times 1 factorial plus, then we get 1 over x squared times 2 factorial plus 1 over x to the third times 3 factorial. And that was my power series. I'll put that in parentheses, plus dot, dot, dot. This pattern continues, dot, dot, dot. Obviously, it's a power series. And then we're going to subtract 1. And we're going to multiply all that by x. Well, notice what happens when we subtract 1. That subtraction of 1 right there from the original problem is convenient because it gets rid of that one constant term. So those cancel, and then we're looking at simply the limit. Let's see if I can get that all on the screen. Then we're simply looking at the limit as x is approaching infinity of x times 1 over x times 1 factorial plus 1 over x squared times 2 factorial plus 1 over x cubed times 3 factorial. And of course that pattern continues. We could rewrite it as a power series if we wanted to, but we're just trying to take the limit. And when we multiply by x, what happens is the first we're going to distribute it to each of the terms. And the first term is going to become just 1. The second term is going to become 1 over x times 2 factorial. The power of x in the denominator when I multiply by x just goes down by 1. So we end up with 1 plus 1 over x times 2 factorial plus 1 over x squared times 3 factorial plus so on and so forth. And so now I can actually take the limit. So I was doing all that just to simplify, but now I can take the limit. I'm going to run x to infinity as x grows without bound. All of the terms that have an x in the denominator, which will be all the terms except that first term in this limit. So they will all go to 0. The dot, dot, dots will all go to 0. And my limit here is simply 1, and I have my result. So my limit of this function using a power series is equal to 1. Okay, let's keep going on this video, keep working with power series and all their different iterations, do lots of different things. So on this one, let's actually take a number and approximate it with the first 4 non-zero terms. So we're going to take a number. It's going to be the square root of e is what we're looking at. But of course, we think of like e, the square root of e is just e to a power. It's e to the 1/2. So the square root of e is e to the 1/2. And I already put our little recall. We can use our power series representation to approximate that. And it says just find the first 4 non-zero terms to approximate it. So we'll do the same thing, but this time, rather than having x in our expansion, we're plugging in a power for e, an actual numeric value on e here to approximate the square root of e. So let's do it. So e to the 1/2 would be equal to the power series from k equals 0 to infinity of 1/2 to the k over k factorial. I'm going to simplify that just a little bit. That's 1 over 2 to the k times k factorial from k equals 0 to infinity. Wanted to mention real quick, we kind of glossed over the fact that we could even do this, but 1/2, remember that the radius of convergence, I did write it over here in my recall, but remember that the radius of convergence is infinity, which means that x can be any number. Of course, you can't use this power series expansion if the x value that you're trying to plug in is not in the radius of convergence. Okay, so anyways, we've got our little expansion here, our power series expansion. We got it simplified, and all we wanted was the first 4 non-zero terms. So we're going to do the same thing we did before. K equals 0. Since we start at 0, the first 4 non-zero will run from k equals 0, k equals 1, k equals 2, and k equals 3 to give us our first 4 non-zero terms for e to the 1/2. And so k equals 0, when we plug in 0, we get 1. When we plug in 1, we get 1 over 2 to the first times 1 factorial. When we plug in 2, we get 1 over 2 squared times 2 factorial. When we plug in 3, we get 1 over 2 cubed times 3 factorial. So turns out, let's put dot, 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 because that does continue. I got my first 4 non-zero, but it does continue. So e to the 1/2 is equal to 1 plus, if I just simplify that, that's 1 over 2. 2 times 2 times 2, we got 1 over 8, not equals, plus 1/8. Trying to do the math in my head there. This is 8 times 3 times 2 times 1 is 6, so 8 times 6. So we get plus 1 over 48, and that continues. So turns out actually that e to the 1/2, the square root of e, which is e to the 1/2, can be approximated by the sum of these first four non-zero terms. This ends up being 79 over 48, which is approximately 1.646, which is actually, if you plug the square root of e into your calculator, this is actually pretty close. And we only had to do the first four non-zero terms. So, it's kind of showing the power here of power series, that we can get these approximations for these irrational numbers by looking at these power series expansions. And in this particular case, we don't even have to go that far to be pretty close. I believe the actual expansion is 1.6487, which we're, within two decimal places by just adding up four little terms here of this power series. Okay, let's do one more. Let's do the sine of 1 and approximate that using its power series expansion. So the sine of 1, of course, again, we can do that because 1 is within the radius of convergence, which is infinity. And our sine of x can be expanded using this power series, or approximated using this power series. So the sine of 1 is simply going to be k equals 0 to infinity, negative 1 to the k. We're going to plug in 1. So 1 to the 2k plus 1, of course, it's just going to become 1. And then that's all over 2k plus 1 factorial. So that is just negative 1 to the k over 2k plus 1 factorial from k equals 0 to infinity. And when we start writing that all the way out, that becomes, let's write out the first four non-zero terms. So k equals 0, k equals 1, k equals 2, and k equals 3. It helps me to have that visual there to see what I'm plugging in. And then we'll keep going. So when we plug in 0, we get 1. When we plug in 1, we get minus 1 over 3 factorial, plus 1 over 5 factorial, minus 1 over 7 factorial. And when I write those out, that's 1 minus 1 over 6 plus 1 over 120. 5 factorial is 120. 7 factorial is 5,040. And of course, those continue. And these are my first four non-zero terms. But if I wanted to approximate that, and actually plug those in, it turns out that sine of 1 is approximately, just by actually adding up those four terms, 4,241 over 5,040, which is approximately 0.841, which is sine of 1 radian within three decimal places. And again, we only had to add up the first four terms to actually get that approximation for the sine of 1. And so it just shows us that we can use power series to do lots of things. So, here we represented functions, we represented values of functions at specific numbers, and even took a limit on this video. So just working with power series, playing around with them, recalling that we have that bank of power series that we've now generated. And we can use that bank of power series. I have it projected on the screen now. We can use that bank of power series to do all kinds of things. On the next video, we'll use this bank to do some integration.